Okay, so last time we briefly started talking about roots and weights. So we will we didn't quite get there, but we started talking about some concepts like compactly algebras, simple algebras, and semi-simple algebras. And today we are going to derive some general properties of these algebras. So, let us say that, let me get the notation right. So, today I am going to follow Georgi's book mainly. So, suppose that x a are the basis. So, in physics, this is often called generators of Lie algebra. G, and we consider the consider an irrep of dimension d. Okay. So now, of course, these are basis elements. So it's not like you can diagonalize all of them simultaneously. Okay, but some number of them you can. Okay. In fact, today let me try one thing. Let me write down the SU3 example on one side. I'll do the general stuff there and SU3 here. So let me just write down. Did I write the basis of SU3 last time? I don't quite remember. Okay. So here they are. So this is, so remember what SU3 is. So SU3, SU3 Lie algebra. Okay. These are 3 by 3 Hermitian matrices which are traceless. Okay. If it is U3, they are just Hermitian. If it is SU3, this is Hermitian and traceless. Okay. Again, in a physicist notation is a Hermitian. In the mathematics notation that we have sometimes used in these lectures, you multiply this by some minus I. All right. So I'll write the following basis. So this okay. So I'll write some triplet of j plus j minus or j1, j2, j3 like objects in the 1-2 plane. Okay. First of all. So by that understanding, somebody should tell me what lambda 2 should look like. So that's 0 minus I 0 0 0 0 here. This 0 is a 2 by 1 0, and this 0 here is a 1 by 2 kind of 0, like that. And then of course lambda 3 would be 1 0 0 minus 1. That's the 2 by 2 block, and the rest is trivial. Okay. So clearly this is an embedding of SU2, okay, inside SU3, okay, in which this column and this row and this element are not doing anything. Similarly, clearly you can use other planes. Okay, just like you have used 1-2 plane, you can use 1-3, 2-3, etc. So let me use that notation. So lambda 4 is like this, in which, so basically now interesting things are happening only in the 1-3 plane, okay, and these guys are not doing anything at all. So in the 1-3 plane, this would be like this, and these are not doing anything. Okay, so similarly, lambda 5 is the same thing, in which the middle guys, okay, are all zeros, and you are left with some 2 by 2 matrix, and in that 2 by 2 matrix you should put the. So essentially, what you are doing is that you are finding 2 by 2 blocks, okay, and putting Pauli matrices in those things. Okay, the structure is clear. Good, and something that I should have called lambda 6, but I wouldn't. Okay, let me call that lambda 8 prime. Okay, and that would be again 0, 0, 0, 0, 0, and here I put the sigma 3 matrix. So what is that? That is 1, 0, 0, minus 1. Okay, and I would continue with this. So now I will choose the 2 by 2 block, which is the 2-3 plane. So I'll first put zeros here, and in the 2-3 plane I would do. So the structure now is getting clearer, hopefully. So I do this, and lambda 7, which is again I would put trivial things here, and then in the 2-3 plane I would write the Pauli matrix sigma 2, and here I can write some thing like this again, which is 0 and 1, 0, 0, minus 1. Okay. Now, if you count the number of generators, you get 9 here. Okay, that would have been okay for U3. Okay, but it's not okay for SU3. Okay, the point is that these guys are not independent. So what one does is to take is not to take this lambda 8. So I will not use these guys, but I'll use one traceless metric, which a traceless Hermitian matrix, which is called lambda 8. It's given by it's just another choice in which I put 1, 1, minus 2, and with a factor of 1 over square root of 3. There is just a convention so far. Okay, we'll talk about normalizations as we go on. Okay, so this is what these matrices are. Clearly, so everybody agrees that these are all linearly independent, right? These are all linearly independent. So this could be a basis, and this is a basis called Gell-Mann basis. So these are called the Gell-Mann generators of SU3. And now let us try to figure out how many of these can be mutually commuting. Okay. So the maximum number of commuting generators, we are looking for the maximum number of commuting generators. In case of SU2, okay, how many commutators could be, how many generators commuted with each other? Nobody.
No.
So J1 did not commute with J2, J1 did not commute with J3, J2 did not commute with J3. So we could take any one of them and diagonalize them, okay, and the remaining guys will be off diagonal. So J3 was taken to be that guy. So here the corresponding concept is that look for the maximum number of generators that you can simultaneously diagonalized. Okay. And in this representation, you can already see what are the diagonal guys. Okay. So, namely lambda 3 and lambda 8. Very good. And so, in fact, by just looking at it, trying out a few things, you can see that that is indeed the maximum number of. You can't make some basis transformation. Okay, this I am not going to do this, in which some other generators among these, okay, commutes with lambda 3 and lambda 8 together. Okay, so this is called a rank. So the maximum number of commuting generators in an algebra is called the rank. Okay, so the maximum number of commuting generators is called the rank. Generators is called the rank, denoted by R. Okay, so, and the conventional notation for these things is to use the letter H. Okay, and this clearly formed by themselves a subalgebra, and this is called the Cartan subalgebra, CSA. So, in any representation, of course, this statement will remain true, that if these are commuting in some representation, these will be commuting in every representation, because a representation preserves commutation relations. Okay. So, in the abstract Lie algebra also these are commuting objects, okay, and this is the maximum number that you can have. So, therefore, in any representation you can choose a basis in which these guys are diagonal. Okay. So, for instance, I wrote these things a little too big. So, this is a 3 by 3 representation, 3 by 3 matrix representation of SU3. Okay. This is also called the fundamental representation or defining representation, etc. Okay. So, here, so what are the basis vectors of this of the representation space? The representation space is a 3-dimensional space. Why? Because it's each of these guys is acting on a 3-dimensional vector and transforming it to something else. Okay, so that basis is 1 0 0 0 1 0 and 0 0 1. And I have just named these things. By the way, so there is another notation that is used, which is these are called the T's. Okay, so the T's are half of the lambdas. Okay, this is just for some more conventional normalization. This is said in that way. So all the T's are half of the original Gelman matrices. So this is what we will deal with. Half T6 is equal to half of that, and T7 is equal to half of this, and T8 is half of that. Okay, so the half and 1 over square root of 3, and so what are my H's here? What's the Cartan subalgebra? Good. So this is what I would call H1, and this is what I would call H2. So clearly, each of these 3 guys is an eigenvector of the H's. Okay. So how are these eigenvectors? So H1 acting on this guy gives me what? H1 acting on gives it 1. So this is 1 times 1, 0, 0. And H1 acting on this fellow is minus 1 times 0, 1, 0. And H1 acting on this fellow gives you 0 times that. Oh, excuse me. Thank you. Like that. Okay. And H2 acting on these, H2 acting on these gives you what? So now look at this fellow. Okay, so this, let me write the 1 over 2 root 3. Okay, so it gives you 1 over 2 root 3. And this fellow is again 1 over 2 root 3, right? I can read off from here. And this is minus, this gives you minus 1 over root 3. So therefore, I can find eigenvectors which I will denote as such, that there are so in this case there are 3 eigenvectors, because this is 3-dimensional representation that we are talking about. Now there are d-dimensional, we are talking about a d-dimensional representation. So I can have d eigenvectors, and I'll explain to you what this mu business is. Okay, this mu satisfies the following property, that when hi for a particular I, so this I ranges from I equal to 1 up to r. So when a particular element of the Kata subalgebra acts on this eigenvector, it gives me mu I, okay, mu I A, mu I A, mu A. Okay, so these are simultaneous eigenvectors of all the h's. Okay, so this A says whichth eigenvector it is, and mu I, okay, is saying that in that eigenvector, okay, the ith Kata subalgebra element will have an eigenvalue mu I A, right? So in this case, what are the mu fellows in this example? So now I'll get rid of the this maths lecture has this lecture hall is a fantastic thing in which you can pull up and down, and inside whatever you have written, it still is preserved. Okay, we don't have that here. So so now this A index, so I will ask for you, I'll ask you to, so this A runs over the dimension of the representation is this, and what is this vector mu for A equal to 1? Can somebody tell me? That is half. So I'll explain why I'm saying this. So I just rubbed off. So remember that, I should say it is this. So this would be my notation. Why is that so? Because mu of 1, mu 1 is this 1, 0, 0. Acting on 1, 0, 0 by H1, okay, gave me the eigenvalue half, okay, which we have just rubbed off. So H1, when it acted on that, it gave me half. H2, when it acts on the same guy, gives me 1 over 2 root 3. Agreed? So now I'll ask for a suggestion what mu 2 is. minus half 1 by 2 root 3, and mu 3 is so 0 minus 1 over root 3. Okay. Let's plot these vectors. So these are all two-dimensional vectors. Everybody agrees with me? So I can plot them on the blackboard, fortunately. Okay. So how do they go? Half and 1 over 2 root 3. So I go here and I go a little bit here. Okay, and this fellow is just reflection. So I go here and I go here. And this fellow is on the y-axis down like this. Okay, and if you really join them up and do your little mathematics, you will see that it's an equilateral triangle. Okay, so we'll come back to this equilateral triangle, and various regular polygons appear in this game of Lie algebras. And but the point that I wanted to make here is that these three two-dimensional vectors, okay, these represent the eigenvalues of H1 and H2, and these are called weight vectors. Okay, so these things, this mu A, these are called weight vectors. How many weight vectors are there? So the vectorness, okay, is ascribed to the I index. Okay, and this is just a label. This A is just labels. How many weight vectors are there? D, because it's a D-dimensional representation. And what is the dimensionality of each of these mu fellows?
The number of the circles.
So R. Okay, so these are weight vectors. These are R-dimensional weight vectors. R-dimensional. And how many of these are there? So how many is D. Okay, these are the important things. Now let us go to so this is true. Yeah.
Just a question. So we always choose the various.
Sorry, just one second. Hello. Hello. আমি ক্লাস নিচ্ছি রে, হ্যাঁ। Okay, bye.
So
yeah, sorry, please go ahead.
Always choose the coefficients and of the generators, and for instance you multiply lambda by half.
Half, why?
So
Yeah.
as to make them lie on this unit circle on the plane. Or some unit sphere. I mean, in this case, this turns out to be two-dimensional.
So I said last time briefly that there is a notion of metrics in the space of Lie algebras. These are given by the traces in the adjoint representation. Okay, similarly, you can take traces of H1, H2 in any representation. So there is a certain convention that you must adopt about the normalization in various representations. Okay, and so that just from sheer convenience that you do these things, and in the most natural convention that you have, so these turn out to be equilateral triangle. Of course, you could say that I could elongate my H1 by a factor of 100, okay, and H2 by a factor of 1 over 100 or something like that. You could do all that, but if you make the so that statement I should make right now, okay, here itself. So we will make this normalization convention. So that's an important issue. So normalization. So normalization okay. So, it is the following, that in some representation D, I choose a normalization in such a way that for all these r number of vectors, okay, that you know, there is this KD guy is independent of delta Ij. So, first of all, I can choose, okay, these you know, the H1, H2, the choice of H1, H2 up to HR in such a way that this bilinear the construct, okay, is delta Ij. Okay, that's point number 1. But that delta Ij could be I dependent. Okay, so there could be something I times delta Ij. Okay, but I want to make my normalization convention in such a way that that's independent of I. Okay, so for each of these guys like H1, H2, H3, etc., trace of H1 square in a particular dimension, in a particular representation, is a given number, which I am calling KD. And for H2 square also is the same, H3 square also is the same, and I have chosen them in such a way that H1, H2 is 0, H1, H3, etc. equal to 0. Okay? Good. So, right, so I will say up to this much about weight vectors. I will come back to these things, and this is my normalization convention in a representation D. In a representation D. Okay. Now, I will talk about some special case of weight vectors, which are the adjoint weights. Okay. They will play a very major role. These are called roots. Okay. So, now I am talking about a special set of weight vectors. That's, so now I am going to talk about adjoint representation, which will lead us to the concept of roots. Now, let me remind you again what an adjoint representation was. In an adjoint representation, the generators themselves could be identified with vectors. Okay, just to remind you, X being thought of as an adjoint representation operator acting on Y. I am thinking of X acting on Y, which is actually a commutator. Okay, so that is by definition, it takes this ket and transforms it to this ket, okay, X comma Y. Let me write in terms of basis so that people are more comfortable with this. So, you can also write this in a more physicsy notation like this. This object essentially is nothing but this, which is being thought of as, you know, as a vector. All Lie algebra elements can also be thought of as vectors. Okay, remember, a Lie algebra is a vector space. Okay, it is for SU3. Okay, there's a 8-dimensional vector space. Okay, so each of these guys can be thought of as a vector, and I can act by another Lie algebra element, okay, to give you another vector. Okay, some other 8-dimensional vector. So that's what this game is. So these are all various ways of writing these things. So now let's say that I write TA acting on TB, what should that be? So it is this TC. Okay. This we have already said before, but I'm repeating this, just jog your memory. Okay. So as a result, FABCs are the matrix representatives of the TAs in the adjoint representation. Okay. This is something that we used last time, and for compact Lie algebras, these FABCs being completely antisymmetric, okay, that told us that the this is a representation in which all the T's, okay, all the basis elements are represented in terms of Hermitian operators. Okay, very good. So now clearly from here you can see that in this representation the following statement is true, right? So if nothing else, you know the following form of the HI operators, okay, in the adjoint representation, namely that H1 looks like a whole bunch of zeros and something which is okay. So what you know is the following. Let me try to prove this also. And some stuff. Okay. What is this notation? This notation is the following: that any H here, okay, and I'm writing this in terms of its action on commutators. So H1, well, H2 up to HR, and then the other guys, okay, the other guys which I will name as E's, all the non-H fellows in the basis of a Lie algebra, which I will choose in a clever way, following what Weil had done and Cartan had done and so on and so forth. Okay, these will be called E alpha, E beta, etc., etc. And so first of all, yeah, so and H1, H2 up to HR and E alpha, E beta. Okay. Okay, just to cut a long story short, what I'm saying is the following, that I can write H1 as the following diagonal operator, okay, in which I have already shown that these guys, this H1, H2, etc. are eigenvectors, namely they are eigenvectors with 0 eigenvalue. Okay. The rest of the guys also I can choose a diagonal basis, because H1, H2 up to HR are simultaneously diagonalizable. Okay. And what I will do is to call this eigenvalues as alpha 1, beta 1, etc., etc. So in particular, if I have HI here, it will have the following structure. It will have an R by R 0 block. Okay. It will have an R by R 0 block, 0 here, and diagonals here, which are given by the following labels: alpha I, beta I, etc., etc. Is this clear to everybody? No? Okay, good. So I claim that I can find simultaneous eigenstates, okay, in the adjoint representation also. What does it mean? That means that these kets, whatever some kets, okay, they will have some eigenvalues. But these are Lie algebra elements themselves. Okay. So let me call it E. So if I say this takes you to this commutator, This takes you to this commutator. Sorry, I forgot to write the commutator. This takes you to this commutator thing, and I claim that this is some eigenvalue. What does it mean? This object is just the Lie algebra element itself.
So why must it be E be an eigenvector of HI for anything that is not within the Cartman subject?
So let me say it again. So keep flipping. Your mind should be flipping between the adjoint representation as a commutator, adjoint representation as an operator. Okay. Think of all the HIs as operators. Okay, acting in some the whatever number of whatever dimensionality of the Lie algebra. So so this is the entire dimension of the Lie algebra. Okay, let me call that D or something, dim G. So this H1, H2, H3 up to HR, they are mutually commuting in any representation. In particular, they are also mutually commuting in the adjoint representation. What does it mean? That means that I should be able to find some basis, okay, in which all of these HIs are diagonal. Is that clear? So I should be able to find how many number of, so dim G, let me give it some name, delta. Okay. I should be able to find out delta eigenvectors, okay, in which every H1, okay, has the diagonal shape. Okay. So H1 is diagonal, H2 is diagonal, H3 is diagonal, HR is diagonal. All of them are diagonal. But specially, I know that if I orient my simultaneous eigenvectors in such a way that the first R of them are H's themselves, then these guys are 0, and these guys are something non-zero, because the HIs don't commute with anything else. Okay, but I have chosen, I can choose them in such a way that I get these guys, any one of these fellows, I can choose in such a way that, how does that follow? It follows from the same thing, that mutually commuting operators can be diagonalized in any vector space. Is that clear? Is that clear to everybody? This is an important concept. Okay.
So you are using the fact that this is compact. When you are saying that there can be simultaneously diagonalized and the common eigenbasis is spanning the whole space, that spanning the whole space part, that is H1, H2, HR, E alpha, E beta, dot dot dot. This common eigenbasis spans the whole space.
Yes.
That part uses the fact that H's are actually Hermitian.
I'm using that fact.
And that means you are using that they are Hermitian.
I'm using the completeness of this in the adjoint representation, and of course the adjoint representation is a finite dimensional representation. It's namely this representation, and this finite dimensional representation can indeed be spanned by the eigenvectors of H1, just H1, let's say,
Yes,
and H2 will have.
Property of them are going into it.
You can do otherwise also. I mean, it's a bit too strong to say that it has to be necessarily Hermitian, but Hermitian will do. It's certainly a sufficient condition. Yeah. So that's correct. So since I have, yes.
Yeah, I'm still confused about this last one. Why can't it be some plus beta E beta? I understand from your argument.
All I'm saying is that these are, let's use the word eigenoperator. I'm saying that you can choose a basis of the Lie algebra in which everybody is an eigenoperator of the H's. Okay, sorry, I forgot to write this. Is this clear? It's important to get it completely clear. Is it clear to everybody what I'm doing here? This is an adjoint representation, means the operators themselves, each of these operators, okay, can be thought of as some kind of a matrix. Okay, this, let's invent some name for this. Delta I don't like, K. Okay. These are all k by k matrices. K is the dimension of the Lie algebra. So I have k by k r number of simultaneously diagonalizable k by k matrices. Okay. So clearly I can choose a basis in which each of these k r matrices is diagonal. But what does it mean in terms of commutation now? Okay. It may, okay, so that is to say, you know, I act by, so these are, so how does one think of a matrix, okay, for an operator? Okay, you write the kets here like this for various alphas, let's say E alpha 1, E alpha 2, whatever, blah blah blah, like that. Maybe I should call the alpha 1, alpha 2, like this, okay, and alpha 1, alpha 2. So you take an operator, act on this and see what linear combination it generates. You take another one, blah blah blah. Okay. Now what is this action of an operator? That's commutation. So you take each one, you commute and you get 0. Clearly it has to be 0. So it's 0 everywhere. 0, 0, 0, 0, la la, 0, 0, 0, 0, etc. Here, by this theorem of simultaneous diagonalizability, okay, you have made sure that it has eigenvalues only. It's a diagonal eigenvalues. What does it mean? That means that when H1 acts on E alpha 1 like this, okay, it picks up something only at E alpha 1. Okay, so that is this statement. That is this statement. Right? I'm choosing this. I'm using this theorem of simultaneous diagonalizability of commuting operators. Okay, but in this adjoint representation, where it means something different. Okay, here it means that if something has this. So let me now introduce the notation. This is the notation that I'm going to use. That if the eigenvalues of the HIs, okay, turn out to be, so I'll call the eigenvalues of the HIs alpha I, and the particular eigenvector which has these eigenvalues, I will denote that by E alpha. Okay, clearly alpha i's are how many dimensional? What is the range of this I? R again.
Rank.
So these are also these alphas are also R dimensional vectors. Okay, is it clear to everybody? And this statement in the adjoint representation, this statement is just this statement. This statement. This is just the same thing as this statement because it's the adjoint representation. Can this space be degenerate? So they won't be, but it will come. At the moment, okay, for a given alpha, there could be multiple choices of E alpha, but it will turn out that it's not so. Okay, these are indeed non-degenerate fellows.
Alphas are k minus r, right? K minus r, the dimensionality of alpha.
Exactly.
Yeah.
Exactly. This K also I don't like. I don't know what I like, but let me call so the number of alphas, the number of alphas is equal to the dim G minus R. Okay, so to sort of make a connection with the weight notation, for the weight notation, what I had was that there were these mu fellows. Okay, and this is A going from 1 up to D, where D was the dimensionality of the representation. Now these for the adjoint representation, these mu guys, okay, are simply 0, 0, 0, 0, etc., and the rest of them are being called alphas. This set are being called alpha. If you wish, you could use a label here, indeed, like that. Okay, this vector and these A's now run. So the total number of entries here in this vector has to be this D for the adjoint representation. So that's dim G. So indeed you have R entries here, and the rest of them has to go from dim G minus R. Okay, good. So the next thing that I want to say, so this, the existence of this basis makes life enormously simple for you, okay, because in this, you know, the it will we will find. So first of all, you know, the notion, the action of H's on these alphas. So what I am saying is that the FABCs are getting more and more simple with this choice. We have made this choice of H's, okay, which are good things, and then we have found some particular choice of the rest of the generators of the Lie algebra, okay, in which the commutation is just this. These are all eigenoperators. So that's one further simplification of this. Very surprisingly, it will turn out that even E alpha E beta commutation, okay, is very simple. Okay, so we will find all that. So eventually, all the FABCs, okay, will turn out to be some particularly simple object, and as a result, this problem of classification of structure constants that I had told you in the beginning, you will see that, you know, you will be able to enumerate what all possible structure constants are possible with this. Okay. Even E alpha E beta commutational relation, you can say a lot of interesting things about them. For instance, it will turn out that E alpha E minus E alpha commutator is along H. Okay, so all right, let's carry on.
So the Gell-Mann matrices are the defining representation of SU3, and now.
So the Gell-Mann matrices by themselves are not the E alphas, but some. So let me tell you what. Yeah, and it's actually very simple. What the E alphas are in terms of the Gell-Mann matrices. Okay, so I will first tell you the result. Okay, so first of all, what are the alphas? Okay. For the Gell-Mann matrices, okay. What are the various root vectors? Okay. Yeah, actually, I need a little bit more technology for that. Otherwise, I can of course do it by brute force, but I need some technology here. Okay. So in the general theory. Okay. So let me first prove the following, that let me first prove a few results, okay, general results. One is that so there's a series of results that I will prove. One is that E alpha dagger is E of minus alpha, and okay, let me prove these things one by one. Just the eigenvalue is minus alpha. Yeah.
On the
remember that the way we are labeling these eigenvectors, okay, which are also Lie algebra elements, by the eigenvalues with respect to the commutation of. So this is the definition. This is the definition of E alpha. This defines what E alpha is. I mean, up to the question of non-degeneracy. Okay, So this tells you that alpha is the thing. So from alpha to E alpha is would not be a unique map if this is non-degenerate, if this is degenerate. Okay, but I'm postponing this and just claiming at the moment that these E alpha guys are actually uniquely determined by alpha itself. So this is this alpha vector is alpha 1 up to alpha r. I'm using just the vector notation for this set.
Oh, so I mean the eigenvalue should be also vector. Basically a point in the vector space. Alpha I.
Yeah.
That also should be a vector.
So there is a label for whicheth alpha it is. That label is implicit here. Okay. So indeed, how many alphas are there? Dim G minus R.
Yeah.
Okay. So there is a label like that. You're right, but I'm sort of suppressing that label. Okay. Good. So let's prove this first. Okay. That if you take the Hermitian conjugate, so first of all, it says that the E alphas themselves, okay, are not Hermitian operators. If you take the Hermitian conjugate of E alpha, what you get is another basis element corresponding to the eigenvalues minus alpha. Okay. By the way, these alphas are called roots. I forgot to say. Okay. So these are weights of the adjoint representation in the way I said it, that if you write down the weights of the adjoint representation with a whole bunch of zeros first and then the non-zero objects, those non-zero objects are called roots. Okay. So how does one prove that? That's actually easy. So you you start with Hi.
We refer to the weight vectors as weights. The weight vectors that you had drawn on this equilateral triangle. And
Yes.
The weights and the weights and weight vectors are the same thing.
Well, the weights are those numbers. Yeah, and the weight vector is the vectorial. Yeah, right. Okay, good. So
so the number of weights is the same as the rank of the Kata-Sabal algebra.
number of weights is the number.
The number of components in weights in a single weight
The
vector.
dimensionality of the weight vector or the dimensionality of the root vectors, all of these are R, the rank of this. But how many weight vectors there are, that depends on the dimensionality of the representation.
That's DVG.
Right. And adjoint representation is something special in which you know that R of them are bound to be 0. So the number of non-trivial weight vectors in the adjoint representation are not dim G, okay, is not D, okay, which would have been the dimension of the thing, but it's that minus R, because R of them are trivially set to 0. Okay, all right. So you have this relation, okay, E alpha. Let's take the complex conjugate of this relation itself. Now HI's, okay, are supposed to be Hermitian operator, okay, so therefore this guy is real, okay, all the alphas are real objects, okay. So now let us take the Hermitian conjugate of this. So you will have dagger I alpha, and if you take the dagger of this here, what you will find is that they switch positions, okay. So you have E alpha dagger HI is equal to that, okay. So this you can write, of course, in this form, that HI is equal to minus. So E alpha dagger is that generator whose eigenvalue is minus alpha I.
So we're taking H to be Hermitian. Is H necessarily Hermitian up to this point?
We have used this compactly algebra thing.
Okay.
So the FABCs are all this thing. So we proved last time that is completely antisymmetric. Did we? I forgot whether we proved that. We did. Yeah. So therefore, in the adjoint representation they certainly are, okay, and I then quoted without proof that in any other representation also they are, for compact Lie algebras they are Hermitian. Okay, good. So therefore, HI dagger I don't have to take because HI dagger is HI itself. So what did we prove? We proved this, okay, that E alpha dagger is the operator with eigenvalue minus alpha I. Okay. So clearly this means that this is minus alpha, because by definition E of minus alpha would be something whose eigenvalue would be minus alpha I, minus alpha I. So it says two things in one shot, that if alpha is a root, then minus alpha has to be a root, and the object that has that root, the generator corresponding to that root is E alpha dagger. Okay. So that immediately says that you don't have to work so hard to know about all the dim G minus R roots. They nicely split up into two halves. Okay.
So dim G R is always even. That's one of the concepts.
Dim G minus R is an even number. Okay. That all will come. So indeed it's true. Let's check it out at least for SU2 and SU3. For SU2 R is 1. The rank is 1. Okay. No, rank is 1. Okay. So and dim G is 3. So dim G minus R is 2. So even number. For SU3 R is 2. Okay. And dim G is 8. So 8 minus 2 is 6. What happens? What I am saying here is that this 8 minus 6 guys nicely split up into E1, E2, E3 and their daggers. Okay. So a whole lot of results you can just derive only about the E1, E2, E3, and the result about their daggers just follow. Okay. And so so there is, so we'll find in the next class that there is a notion of positive roots and negative roots. So the space of roots, okay, you can split up into positive roots and negative roots, and a whole lot of results you can derive just about the positive roots, and the negative result about the negative roots will simply follow. Okay. So this result once again proves two things. If alpha is a root, then minus alpha is a root also, because by construction I have demonstrated that there is a Lie algebra element, okay, in which is an eigen operator of HI, okay, and the eigenvalue is minus alpha. Okay. So this is proof by construction that minus alpha is also a root. Okay, good. Just a word about normalization once more, that note that.
So just one more question.
Yes.
This EAs will in general be complex linear combinations of the original defining.
Oh yeah, I forgot. Thank you. I forgot that I have generalized today's discussion, okay, to complex Lie algebras. I am allowing complex linear combination of things because these E alphas, okay, they are not Hermitian by themselves. The Gell-Mann matrices, no, the Gell-Mann matrices, you could take them to be just real Lie algebra, okay. Just like that doesn't matter.
You could use complex coefficients.
The generators can have complex fellows in them, but you could spend your life by taking only real linear combination of Pauli matrices. However, if you want to do this kind of thing, diagonalize, okay, the eigen operator thing, then you have to, for example, what I am saying is that J1, J2, J3, okay, provide you with a basis of the real Lie algebra SU2, but staying within the real Lie algebra, okay, you can't diagonalize the action of J3. In order to diagonalize the adjoint action of J3, you have to go to J1 plus IJ2 and J1 minus IJ2. Okay. So you jump to the complex Lie algebra And once you go to the complex Lie algebra, you know, the analysis of SL2 and analysis of SU2, these get identified, and eventually in order to you know, make some of your results back again, you have to declare which are the Hermitian operators, okay, and how the Hermitian conjugation goes. Okay, so such as these. Okay, here it says that J plus dagger is J minus in SU2. Okay, that is what follows from the Hermitianness of the representation. Okay, in SL2, if you want to go back to the, okay, so this probably to the real section called SL2R, okay, there J plus dagger is not J minus, okay, J plus dagger is J plus. All right, okay, in order to have a unitary representation. Okay, that's just a thing about normalization. So E alpha so remember that E alphas and the HIs, okay, they are kets, they are simultaneous eigenvectors, okay, of this H1 or H2, etc., etc. Therefore, all of these guys are orthogonal. That much is clear. All of these guys are orthogonal. So therefore,
coincide with the inner product of the operators, corresponding operators.
yes, 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 indeed. So these fellows, okay, these fellows are related to trace in the adjoint representation of E alpha E beta. This actually you can prove sorry, I forgot to this. Whatever appears on this side, the dual vector that comes with a so this is my so what I'm saying is that from the fact that these are simultaneous eigenvectors, these E alpha or E beta, these kets are simultaneous eigenvectors of H1 or H2 or any of these Hermitian operators, means that these satisfy this orthogonality relation, and similarly HI fellows with E alpha, they are of course 0, and HI. So you can just choose them to be. So this is proportional to delta alpha beta, this is proportional to delta ij, proportional to that. And what you do is to say that, well, these proportionality constants are all identical, lambda, okay? And you can take this to be 1 if you wish, okay, by an appropriate rescaling. But the main point here is that throughout the representation, these guys, okay, so that is to say the trace in the adjoint representation of this has to be lambda alpha beta, and the trace in the adjoint representation of HI, Hj are also lambda delta ij. Okay, so that completes my, and of course Hi with alpha, E alpha E betas, that's equal to 0, because this, the norm has to be I mean, you can prove this by showing that if you take this guy as a definition of a scalar product, okay, in the adjoint representation, then they satisfy all properties of a scalar product, including positive definiteness and so on and so forth. And indeed, the adjoint representation vector space, okay, is then equipped with that scalar product. And it is with respect to that scalar product, you can say that these are all orthogonal. Okay, so let's not. This can be proved. This can be proved by some jugglery with axiomatic properties of these. Basically, the compactness of this Lie algebra plays a role here. That the compact Lie algebra, in fact, one of in some ways is the definition that this quantity defines for you for a compact Lie algebra positive definite scalar product. Okay. All right. Okay. Let me. Why? Sorry. It is a killing form.
So as a part of a real vector space,
Right.
when we thought about it as a real vector space, then we had trace adjoint representation of E alpha times adjoint representation of E beta.
Right.
That was the killing form.
That's right. So I'm saying that when I'm in the adjoint representation, so the correct scalar product to use in the adjoint representation vector space is that one.
Now with the dagger, so if we were doing the killing form, so say kappa alpha beta, we would have written trace of adjoint representation of E alpha times adjoint representation of E beta.
Right.
And that was for compactness was negative definite, or with I is positive definite. Now, here
Where did this dagger come from? Yeah, so here I am indeed generalizing from the real section to the complex section without proof. It is true. It is true. The killing form, that's an absolutely valid point. The killing form is defined with respect to trace of adjoint x, y, okay, and that is x dot y. Okay. So that indeed is about the real section of a Lie algebra. Okay. I have complexified this and I have generalized the killing form to this thing with a dagger for the first argument without proof. Yeah, it's true, but it can be justified. Okay, let me say that. Okay, good. Let me prove another important relation, which is that E alpha, E minus alpha is equal to alpha I H I. Okay, so if you take a linear combination of E alpha and E minus alpha, okay, if you take the commutator of E alpha and E minus alpha, it's not another E, okay, it's an H. Does it remind you of something? J plus comma J minus is equal to. So this object happens in all the algebras, okay, not just in the SU2, but in everything. So how does one prove this? So basically, what you have to show is that the weight corresponding to this. So if you think of this as E alpha acting on E minus alpha, okay, that should have weight 0. Okay, so let me say what my strategy would be, that I construct this vector, okay, and I want to show that H's acting on this, okay, give you 0. Okay, so Hi acting on this vector gives you 0. This is what I want to say. If that is the case, then this fellow must be some linear combination of because of the maximum number of commuting generator thing. You cannot invent another commuting generator inside. So if this so happens that Hi acting on this combination gives you 0, then this fellow must be of this form.
And they are not necessarily the same eigenvalue.
Oh, the same alpha.
Same eigenvalue.
Same alpha. If it is E alpha acting on E beta, okay, then it can be some E. But if it is E alpha acting on E minus alpha, okay, or E alpha acting on E alpha dagger, which is the same thing, that has to be an H. It has to belong to Cartan subset. Let's see how to do that. So I want to show that this is equal to 0. So in other words, now writing this out in terms of commutator. So this is the commutator action minus alpha. This object I want to show that this is equal to 0. Okay, Jacobi identity, that is correct. So this fellow is, so I know that this object plus E alpha, E minus alpha, Hi. So cyclic permutation of this, right? So then E minus alpha, comma, Hi, E alpha. This is equal to 0. Okay, but what is this? Can anybody say what this object is? So this is alpha I Hi, correct? Because Hi acting on E minus alpha would have been minus alpha I. So in this combination it would be alpha Hi. Oh, sorry, excuse me. Sorry. Thank you. Like that. Okay, and this animal is alpha I E alpha. So the alpha has come out of the commutator. So first you have the E alpha E minus I alpha combination, and then you have E minus alpha E alpha combination, so that this cancels out. So that's equal to 0. So therefore this equal to 0, this equal to 0. So therefore E alpha E minus alpha, this combination is equal to okay, so this some linear combination. So therefore it has to be of the form some beta I alpha I equal to 0. Now in order to show that this beta I has to be alpha I itself, what do? You take the inner product, exactly. Okay, so beta I is, okay, so let me write this thing again in terms of if you wish, what I have found is that this, okay, let's take the inner product of this. So inner product means that trace in the adjoint representation. Okay, that's what I have to do. So so H's are normalized only up to, so for this purpose let me just ignore this lambda equal to 1. Okay, so then I'll just take a inner product, multiply both sides by H and trace it. Okay, so the beta I then would be Hi trace and E alpha E minus alpha, like that, and then you can sort of use a cyclicity of trace to make it into trace of E minus alpha and Hi E alpha. It's just some jugglery with cyclic property of traces, and then this animal is alpha I E alpha. Okay, but by our normalization, E minus alpha clicks with E alpha under the trace with a factor of 1. Okay, so I got beta I is equal to, so the alpha comes out, so you get beta I equal to. So this is an important result, that E alpha commutator with E minus alpha gives you. So I'll prove the last interesting result now. So we proved this. Okay, and it's clear what. So as I said, this is J plus comma J minus is equal to J3. Okay. I'll write down the SU3 things perhaps. Okay, so before going to SU3, let me write down, basically what the idea would be to, if I don't get into that thing, the idea would be to discover little SU2s inside any big Lie algebra. Okay. So in SU3 we will sort of work out how to do that kind of thing. I already more or less indicated by introducing this lambda 8 prime and lambda 8 double prime matrices, which I didn't use eventually. But so there are these little SU2s hanging around there. And
is it possible for any Lie algebra discovering little SU2s?
yeah, that is how this game is played. Okay, good. So now I'll prove a recursion relation, which is like a recursion relation that we proved for SU2. So this recursion relation is the following. So this is probably the most important result of today. So, I forgot to say that, I forgot to, sorry, excuse me. So, as you might have guessed already, that the E alphas might act as raising and lowering operators, okay, because J plus and J minus do such things. So E alpha and E minus alpha might do such things also. So what does it mean? Now I go to some other representation, some arbitrary representation, which are given by an act by E alpha on mu, okay, mu A. Let's say I'll ignore this Whicheth weight vector and just act by this, and I claim that this is up to some normalization constant. This will be mu plus alpha. Okay. So this will be proportional to mu plus alpha. How does one see that? So just act by Hi on this. So we will act by Hi on this, so which is essentially the commutator plus E alpha Hi acting on mu. Okay. So this part gives you mu, right, I. So Hi acting on mu gives you a C number, thus mu I, okay, and then E alpha just passes through. So this part is that, and this guy here is alpha I E alpha. So overall I get alpha I plus mu I E alpha mu. So this, if I think of this E alpha mu as a new vector, then Hi acting on this, so Hi acting on this gives me mu I plus alpha I. So recall that Hi acting on mu gave you mu I acting on mu. That was the definition of my weight vector mu. Okay. Now when I apply E alpha on that, okay, I get this eigenvalue. So therefore, this fellow here is clearly proportional to, okay. So it shows two things. First of all, there has to be a weight of mu plus alpha, okay, because by construction I have constructed it here. If mu is a weight, then mu plus alpha is another weight, okay, and so it is proportional to this thing, and but there is an exception. there is an exception to this rule. This construction seems to show that, so again, claim is that if mu is a weight, then mu plus alpha will always be a weight.
And highest weight will be
up to highest.
Good. Unless it kills it. Okay. So if this guy is 0, okay, then my claim does not work, and that is how the dimensions get a finite representation. Otherwise, of course, if mu is a weight, mu plus alpha is a weight, mu plus 1 million alpha is also a weight, etc., etc. So it will go on forever, and similarly it will go down also forever. Okay. So okay. So by the way, so this alpha is a vector. So there is nothing like positive or negative. So this is true in any which way. Okay. And so E minus alpha acting on mu will give you something which is mu minus alpha. Okay. So I will call this vector as my notation would be that it is n alpha mu. So this notation is a second argument says which weight vector it is acting on, okay, and the first argument says what root is acting on it. Okay. So this n alpha mu, that's my definition of n alpha mu. Okay. So with this I am now going to prove to you the following result, which is n alpha mu minus alpha square minus n alpha mu square is equal to alpha dot mu. Okay, so this is an important thing. It's a recursion relation which says that if I know what n alpha mu is, okay, then I can derive what n alpha mu minus alpha is. Okay, so I can go down, okay, in mu minus alpha, and I can define what I can derive what this. Okay, so that trick is the following. So first of all, let us say that I have some weight vector mu, and I act by E minus alpha. Okay, and where do I reach? This would be, what is the weight of this? Mu minus alpha. Good. And what is the constant that I will pick up here? That's right, n minus alpha mu. Okay. And alternatively, I could start from here and go there. Starting from mu minus alpha and applying E alpha and reach here. What would be a constant that I pick up on this side? So it would be n alpha mu minus alpha. But these two matrix elements are just conjugates of each other. So therefore, we have proved that this animal is the complex conjugate of n alpha mu minus alpha. Okay. So now let's have a little more fun with this. Okay, since I am not going to reach SU3 today, I will use this part as well. So I start from mu, I go down and I come back. I go down and I come back. Okay. So that means what I am doing is that I am acting minus alpha first and mu on mu. Okay, I am now not writing the arrows anymore. These are understood to be this thing. Okay, so the matrix element for this is that Okay, and so can somebody tell me what this matrix element is? So I have reached down, and in that process I have picked up n minus alpha mu.
In minus alpha mu mod square.
Very good. So it's n minus alpha mu mod square. Mod square.
Just the dagger. E minus alpha is dagger.
Exactly.
Here.
That is why. That is why. That is why it's mod square, which of course by our result there it is also n alpha mu minus alpha mod square by the result here. Okay. On the other hand, you could start from okay, so let me just say roughly. So you got the idea of this. So I will do the following operation: E alpha commutator E minus alpha matrix element on. So now with this kind of manipulation, you can sort of see more or less easily that I will get minus alpha mu mod square this way and n alpha mu mod square this way, and I will use this result now. That is, this is alpha mu minus alpha mod square this is clear, right? So what I am doing here is apply E minus alpha first. I get this, but that is by this little lemma, it is this way, and here I am applying on the other side I am applying E alpha first. So is that. But what is this object? I know this is something that we have proved, that this is alpha I h I. Okay. So therefore, and h I is acting on these mu's are just mu I. Okay. So therefore I proved that this is the same as alpha I mu I. Now this clearly has the form of a recursion in mu. Okay. See, this was not very useful because this was not like a recursion in mu, but now the alpha remains the same and mu is recursed. Okay. So we can do a recursion in mu now. Okay. So if I know this normalization for mu, I can so what does it say? This is something that we did for SU2, but not so much in detail. But let me just tell you now what is the what is the consequence of this. This will tell you the general Lie algebra counterpart of the statement that the J value of an SU2 representation is half integral. Okay. So that's our recursion relation. This is our recursion relation, and we are going to use this. So we are going to look at the tower of a single alpha. Starting from a single mu, we are going to go up and down. Okay. So start from mu. So E alpha, right? Mu plus alpha, etc. till it hits the maximum, mu plus p alpha. Okay. So I'm going to use this on all at each of these levels. So I'm going to use this at the level mu, then mu plus alpha, mu plus 2 alpha, etc., etc. So when I apply this condition, when mu is mu, then I just write it. Okay. So that is that alpha mu minus alpha. So I'm just repeating what I wrote. Minus n alpha mu whole square is equal to alpha dot mu. Alpha dot mu. Now at this level, I replace this mu minus alpha by mu. So I have mu by mu plus alpha. Okay, so I'm writing the same relation, okay, in which mu is replaced by mu plus alpha. Of course, it's true over there as well. So what is this now? So it is alpha mu plus alpha is, so this becomes that, and this becomes mu plus alpha mod square, and here what happens is alpha mu plus alpha. Okay, and you keep doing that up there and down all the way up to wherever much you can. So this is mu minus alpha and mu minus, let us say, q alpha. This p is an integer and this q is an integer. What I am doing here is inside an arbitrary Lie algebra, I start from some weight vector mu, okay, and I latch on to one particular raising operator, okay, E alpha, and I go on up. It has to end at some point up there, and it has to end at some point down here. Okay, the number of steps I go up, I call that p, and the number of steps I come down here, I call it q. Okay, and I write this recursion for everything, and I add them up. I add these things up. Okay, so what happens on the right, this side is mu minus alpha, and here it is mu minus q alpha, and up here it is mu plus p alpha. Right? Now, when I add these things up, you can see this cancels with the next fellow, etc. This cancels here, etc., etc. So you get 0. Everybody cancels here. Okay, so you get 0 is equal to the sum of all these things.
The last is also common among do they also cancel?
Everybody cancels. The last term cancels because of the following fact, that the n value acting on that is 0. So that's an important issue. You might have thought that something gets left over, but this quantity by definition, okay, mu plus p alpha is 0. This is something that would have been non-zero, okay, if this mu plus p alpha could go up. Okay, the fact that it's not able to go up means that this normalization, you can define this quantity, this object, okay, as 0. Okay, so that's another way of saying that it's actually gets killed. Okay, so now so how many Jesus yeah, how many alpha dot mu terms are there? P plus q plus 1. So you get 0 is equal to alpha dot mu into p plus q plus 1, and here there is a sum over some arithmetic progression which you can do, and those are all proportional to alpha square. Okay, so what you get is that it is alpha square, and there is no alpha square at this level, and there's some 1 plus 2 plus up to p, and here there's some 1 plus 2 plus up to q. Okay, so it is p into p plus 1 divided by 2 minus q into q plus 1 divided by 2. All these alphas come with minus alpha square. So that's your result, and you can simplify this a little bit to give you. So believe it or not, this has a p plus q plus 1 factor. This is equal to that. This is alpha dot mu and plus alpha square by 2 p minus q. like that. Okay. So therefore, what you get is an important observation that alpha dot mu divided by alpha square is equal to q minus p by 2. This is some non-zero object, so you can just get rid of it. So you get something here. Q and p were meant to be integers. So therefore, this object has to be a half integer. So in an arbitrary compact Lie algebra also, okay, this combination alpha dot mu divided by alpha square, okay, has to be a half integer. Now you should go back to SU2 and show that this is precisely the weight here. You know, this is like the m value. Okay. So this is what's the range of. So we'll explore this in more detail. But let us just write down finally what this quantity means in case of the adjoint representation. So in case of the adjoint representation, so for adjoint representation, it means that, of course, now the mu's are alphas themselves. Okay. So if mu itself is alpha, then it's 1, there's no big deal. But any other alpha, so alpha dot beta divided by alpha square must be a half integer, half of an integer, not half integer, but half of an integer. So but you know, if this is true, then clearly the other thing also is true. You could do the entire analysis here starting with beta. Okay. So this also is half of an integer. Okay. So therefore, you can now multiply these objects is equal to 1/4 of an integer. Right. But what is this? This is a square of this. So this is the angle between alpha and beta, the square of the cosine of that. So this is the cosine square theta is equal to 1/4 of an integer. So if you applied Cauchy-Schwarz inequality right here, you would have seen that this integer here can at best be up to 4. Okay. So let's write out the possibilities. So cosine square theta. So this gives a very strong restriction on the possible Lie algebras. Okay. Namely, the roots have these angles. Okay. So what are these things? So this object, this integer here, let me call this integer as something, n. So n could be 0, 1, 2, 3, 4, and cos theta, that's theta. Anybody remembers their trigonometric tables? So this is pi by 2, which I call 90 degree. This fellow is 1/4 of 1. So the cos theta is 1 over square root of 2. Sorry, I said something wrong. It's 1/4. So yeah, it's 60. 60 degree or 120 degree. 2.
So you are restricting the values of theta between 0 and pi, right?
I'm restricting the values between, yes, I can do that. I can do that indeed. So a little bit of the technology of positive roots will come into that thing. Yeah, that I can do. And 0 degree and 180 degree. We'll encounter all these angles as we go along in various. These are related to the structure of Dynkin representation of roots, and so that's it. This is it. Whatever the complicated Lie algebra is, blah blah, whatever it is, their roots, okay, satisfy this property. So this already tells you a lot about the possible structure constants. Remember, the roots, okay, actually encode structure constants, okay, in that particular basis that we talked about. What we have not talked about today is what happens when you commute E alpha with E beta. Okay, we'll come to that, okay, in the next lecture. So we already know H with H, H with E alpha, and E alpha with E minus alpha. So we need E alpha with E beta. Then we are basically done. We have then specified all the structure constants. But up to whatever we are, excuse me.
Because it can't be a nice algebra, so it has to have something with including H.
What do you mean?
EIEJ
Hmm.
commutator. Suppose it is something EK. Had it been something like this,
Yes.
then they are creating a nice algebra.
Everybody has to include an H. No, E alpha with E beta, of course, will be some E gamma, no doubt. E alpha with some other root vector, okay. Of course, we'll have to give it H. So what you do know is that E alpha with E beta must give you E alpha plus beta, because it's the raising operator. So think of the second guy, E beta, as a vector, and the first guy, E alpha, okay, as an operator. So E alpha acting on E beta, okay, raises the weight of the E beta, which was beta, by alpha. So beta plus alpha. What you don't know is the normalization. So E alpha commutator with E beta must be proportional to E alpha plus beta. Okay, that much we already know. Okay, and what you don't know is the is the normalization. Okay, the other thing is that you might be wondering about, since we went up and down in case of representations, we went up and down along a single alpha. You might go this way, that way, and so on and so forth. So what all happens for a weight for a representation space is not clear. But tomorrow we will more or less, the next time, we'll more or less chalk out the adjoint representation at least. Okay, the whatever all you can say about. This was a bit too abstract. I thought that I would work out SU3 for all these steps here, but next time I'll also do the SU3 examples. Then everything will be clear. Okay, on Friday.